Today we are very happy to have Artan Sheshmani to tell us about higher rate black sheaves and Vafa-Witten invariants. Let's welcome Artan.
Thanks for inviting me to this seminar. So I will give a talk about the paper that we recently put on archive. So this is a paper with Professor Yao. We have worked out several of these things during the past years. All one way or another, they have this same words in their title. So this is actually a continuation of this long project that we have. So let me just tell you a little bit about geometric setup of the problem. So Kamran is here. If you have questions, you can ask him.
No.
So okay. So here is the geometric setup. So let S be a Riemannian manifold, and we fix a compact digging G and a principal G bundle on S. Let's call it P, and then let us let A of P be defined as the set of all G connections on this principal G bundle P, and with values in adjoint of P, and let the omega I, these are just notations, omega IGP be the C infinity I forms on P, again with the values in the adjoint, and let omega plus, which is a subset of omega 2, the two forms, be the self-dual 2 forms with respect to the Riemannian metric on S. With respect to the Riemannian metric on S. So Vafa-Witten equations are equations which are written in terms of these ingredients. So in terms of S being a real manifold, for me, the S is going to be a Kähler complex twofold, complex surface. So the Vafa-Witten equations are basically, one way of looking at them are maps from AP to omega plus self-dual 2 forms and 0 forms to omega plus of GP times omega 1 of GP. These are realized as maps like this, given by equations, and I can actually tell you what these are. So let us pick some self-dual from B, and some omega C infinity function gamma, and some connection induced by the principal, some connection on the principal G bundle P, let's call it D of A, and that will be taken to F plus of A, curvature 2 form, induced by the connection of 4 plus certain kind of a Lie bracket of B with itself. So this is the Lie bracket on the Lie algebra of the G bundle, and then another bracket D and gamma. dA of gamma plus dA star of B. So this is basically data. But I can write it in terms of actual equations, and for us really, we are doing everything complex theoretically, so let us make an assumption that S, the form manifold, is a Kähler twofold, complex two-form, and this is for us, anyway, the problem that we study. So if S is a Kähler surface, is a Kähler complex surface, so that means that S is going to be coming with a Kähler form, omega. Then the Vafa-Witten equations can be written, then the Vafa-Witten equations can be rewritten the following way. So in some sense, I can rewrite all of these ingredients in here complex theoretically. So it will be something like this. So the curvature 2 form induced by the connection 1 form has a Hodge decomposition. So the 0,2 part of it, we would like to be equal to 0. And then 1 part times omega plus phi bar, we would like that to be equal to some topological constant times identity over E of omega star, and omega square, and I will tell you what this E is, and then del bar over A of phi, we would like to be equal to 0. And I need to tell you what these are. So here, phi basically is an element of 2, 0 forms with values in the complexification of the eigenfunction, like that. And another assumption that we are going to make is that we would like G to be either UR or SUR. So that means that our principal bundle is going to be the frame bundle. So frame bundle for a Hermitian vector bundle, which I would call E in here. Okay. So in fact, the first equation the del bar, actually the first equation tells you that you can expect having an integrable holomorphic structure on the spectral bundle, so you would be looking for holomorphic bundles. And this phi you can realize as in some sense as a Higgs map. So then let me write it down. So the first equation defines an integrable holomorphic structure on the spectral bundle E, and with respect to which phi, the map phi, is also holomorphic. Okay, so this is what we would like to have, and now maybe the second, so this is, let's look at this equation. So since the second equation is a moment map, it's a moment map for the gauge group action, we can expect that in some sense we can expect from some kind of infinite dimensional Kempf-Nest theorem, we can expect that solutions to this equation, of course, modulo UR or SUR gauge transformation are given by holomorphic pairs.
Which part is the moment map? Which part is the moment map?
Second part.
What do you mean second part?
The second equation is the moment.
How is an equation a moment map?
Yeah.
He's asking how an equation is a moment map.
Hmm?
He's asking Oh, and the equation is a moment map. You have to explain.
Yeah, moment map should be some map to G star.
Yeah, so then you look at the moment map, you have the gauge group, you take the tangent, then the Lie algebra of gauge group embedded in the tangent, dualize it, you're going to map from the cotangent onto the dual of Lie algebra. Take the quotient, look at the preimage of 0, you get the equation. But anyways, I'm not going to spend so much time on this one. So what is
Can you motivate
important?
these equations somehow? Can you motivate these equations somehow?
I probably will not do it because then I wouldn't have time. Because it has to do with modular constructions and things like that.
Well, one motivation could be just saying it's a 4D version of the Hitchell equation, if you want the formalization.
Yeah, that's right. It is. And basically, this construction I told you also is the construction of the modular space of Hitchell pairs. Okay.
So this is some symplectic quotient that these equations describe?
Is it some symplectic? Yeah, it is very similar to symplectic quotient. That's right. Yes, that's right. So solutions to these equations are given by holomorphic pairs like this. So this is basically our holomorphic pair, like that, which satisfies certain stability. Okay. And now, if this is your surface, I think there is this old story that, I mean, the stability that these things actually satisfy are going to be the Higgs stability. And there is this obvious construction for those of you who are working on this, that if you have some Higgs bundle, which is stable on the variety here for us being the complex projective for Kähler surface, then you can apply this spectral construction and you can get a one-to-one correspondence between set of these objects and some sheaf or some locally a bundle, so some sheaf on total space of the canonical bundle of the surface. So there is this correspondence between surface theory and threefold theory. You give me a Higgs bundle on the surface, so one of these guys on the surface, the spectral construction actually tells you that you can get modules on the threefold, which is given by the total space of canonical bundle here, which are somehow supported on the surface. And these modules are not going to be bundles anymore because they are supported on the surface, they are torsion, their support is lower dimensional, and these modules are what we will call sheaves. So in the language of the string theorists, if you like, Higgs bundles like this on the surface correspond to, in some sense, D4, D2, D0 branes on this non-compact threefold, which wrap the base divides. So moduli space of Higgs bundles, which is the moduli space solutions to Vafa-Witten equations, can be realized as the moduli space of D4, D2, D0 branes on the non-compact threefold with the correct Chern character and so on, or brane charges. So via this correspondence, let me actually tell you a little bit about that moduli space, and then we will come back to the Higgs bundles. The whole point of my talk is actually going to be that in order to count solutions to Vafa-Witten equations, we are algebraic geometers. We need to construct machineries that even make our integrals well-defined. And we are going to use this, what is called Donaldson-Thomas theory. So we are going to be looking at moduli space of objects on the non-compact threefold. And via some localization, we are going to count those objects. Okay, so let me talk a little bit about this non-compact threefold. So localization of Higgs bundles on S as torsion sheaves on total space of canonical maybe I can use canonical this way to easier notation, which I'm going to call X. Okay, so I will tell you just a little bit about this moduli space and then make some example and you will see what's the correspondence. So this is a threefold, and it is non-compact. It has a compact part, which is our surface, and we are assuming that S is as an algebraic variety, we are assuming that this thing is a smooth projective surface. Projective means it has a nice embedding into a projective space. Okay. All right, so now on this moduli space, here is what we are going to do. So let L be a line bundle on S such that sections of L tensor with canonical S inverse are not going to vanish. So I'm going to construct for you, actually, let us actually make this even more general. Any line bundle works, but what relates to the Vafa-Witten theory is only the case where this L is going to be the canonical bundle, because Vafa-Witten theory is a construction of a theory on the surface, and then the spectral construction gives you the non-compact theory. But our theory is more general than this. Any line bundle on S gives us the modules that we would like to have. So you have this, and then let X be defined as total the space of this line bundle on S. Then X is non-compact, and if you calculate canonical bundle of X, it is given by pullback of L inverse times canonical bundle of S. This is just a formula. In particular, if L is equal to the canonical bundle of S, then you will see that the canonical bundle of X will be the pullback of O. They will cancel each other. So then K of X will be O of X, and X will be a Calabi of threefold, which is non-compact. Okay. So now some facts, maybe a fact. This is for those of you geometers or algebraic geometers, or if you took the algebraic geometry course in graduate school. Here's a fact from Hartran's book, that if I push forward the structure sheaf of X, we call it the structure sheaf, but it's basically just a trivial bundle of holomorphic functions defined on X. Then we will get some infinite sum of L to the minus I, basically. It's a non-compact threefold. You take its structure sheaf, you push it onto the surface, and if your X is given by line bundle on S, the pullback of this thing will be some direct sum like this. The module that you will get down there will be a module over symmetric algebra of the fibers of this push forward. Now, one fact which we are going to use, and I mentioned it earlier, is that obviously there is a torus that dilates the fiber of this line bundle. So this object in here, this vector bundle right now over the surface that you get here, you can realize as a graded module, because every factor of L carries a C star action with a certain character. So this is a graded module. And in fact, in the literature, in order to keep track of the weights of these pieces, you can also write it like this: T minus I, where T is a trivial bundle bundle on S with C star weight 1. It's just a trivial bundle, but it has a non-trivial equivariant structure. It's just to tell you that when you take modules from the non-compact threefold and push them forward, which graded piece of this graded module down there they fall in. Okay. Now, on this geometry, we are studying the algebra-geometric analog of these D braids. So, algebra-geometric analog of D4, D2, D0 braids. As I told you, Higgs bundles on the surface correspond to objects like this, torsion objects on a non-compact threefold. So what are these things? For us algebraic geometers, these are coherent sheaves. Coherent sheaves with support not on all of X, because X is 6-dimensional, but support on S. Well, there is an abelian category of coherent sheaves on X, and we are interested in a subcategory of this abelian category, which is the compactly supported coherent sheaves. And our modules on X are going to be picked from this category. Okay? So, we define a slope function. As I mentioned to you, the Vafa-Witten equations already tell you that via some Kempfness type theorem, the bundles that you get down there need to satisfy certain stability conditions. Same thing in here. If I have a Higgs bundle which is on the surface, which is stable, I would like the corresponding sheaf on the non-compact threefold also to be stable. So we pick some kind of a slope function. So on this category. So we look at all the non-zero sheaves in this compactly supported sheaf, category of compactly supported sheaves, and then define some kind of a slope function on it. What is the slope? For any E in this category, the slope of E is going to be like, those of you familiar with differential geometry, it's very similar to the slope of vector bundles. So it is the C1 of the push forward of E times H divided by rank. So you have some sheaf compactly supported on the surface, you call it E. You can push it forward like how I pushed forward O. You can push forward any sheaf onto the surface. This is the push forward. Then you take the first term class of that, and then you need to get a number. So this is element of first homology. Let H be C1 of the ample line bundle on the surface. This is the thing whose sections are given by homogeneous polynomials of degree 1 on that surface. And this is the degree of the sheaf, very similar to the degree of vector bundles. And then you can divide by the rank of the vector bundle. This is the slope. Okay. And this is slope is the one that we are going to use for our moduli space. So mu H is going to defines a slope function on this category, and so with respect to which I can define a moduli space of sheaves in that category which are stable with respect to the given slope. So let MH of X with something that I'm going to fill in here be the moduli space of mu H stable sheaves, or if you like D4, D2, D0 branes, which are picked from the compactly supported sheaves on X, and I'm going to fill this here with a Chern character vector. So where Chern character V given by as follows. So our sheaves, this is our threefold, this is S, this is the line bundle, and our sheaves are set theoretically supported on S. They look objects like this, they're torsion. And if you read off their Chern character, their D0 brane charge is 0, and then they have some Chern character in here, let's say R. This is their rank times the fundamental class of X by a Poincare duality, and then some curve class and some Euler characters. So this is an element of H2 of X, and then H4 of X, and this is H6 of X. So this is in the language of physics, the brane charges. And for us, it's just a Chern character we need to get a well-defined connected component of a certain modular space. Okay, so this is our modular space.
Why do you want H00? You counted H00.
Yes, because we are looking at torsion sheaves. So if they are supported on all of X, they would have some non-trivial rank on X. And their H0 brane charge would be non-zero.
So 0d6 brane charge.
Yes, 0d6 brane charge, some number of D4 brane, and then so these are honest to God D4, D2, D0 branes.
Are these H2, H4, H0 or Z integer class?
Yes, good. Yeah, so I would like them to be with integer coefficients. So these are integral classes. So we would like to give a mathematical definition of counting the Vafa-Witten solutions. And we are counting them via looking at torsion modules on the non-compact threefolds. I need to tell you what does it mean counting, really. I will make an example. So what does it mean, meaning of counting sheaves? What does it mean counting? Well, suppose that you have a moduli space. Okay, so suppose you have a manifold. Suppose you have an m-dimensional manifold, like that. And you would like to associate to this manifold a certain invariant, certain topological invariant or deformation invariant. You deform the manifold and this number doesn't change. One of the famous ones is Euler characteristic of this manifold. You have two ways of computing Euler characteristic. One way is triangulate the manifold and count the number of vertices and one edges and two simplices and three simplices and so on and so forth. Or we can use techniques in differential topology, and this is something that in graduate school everyone learns. We can integrate over this manifold the top Chern class of a tangent bundle, maybe with a minus sign. This is the formula for Euler characteristic of a manifold. This number doesn't change even if you deform the manifold. Okay? So now we are going to define some kind of thing like this, except our space is a moduli space. I called it mx. So instead of this, I will replace it by a moduli space of certain sheaves or D branes on X with fixed given Chern character. And I would like to define some notion of Euler characteristic for it. Okay, maybe some kind of a virtual Euler characteristic. The reason for which is that this space is not a manifold. For instance, on this manifold, on this space, there is some sheaf, which fiber-wise over every point of the space understands deformations of the points that the space parameterizes. But this sheaf is not going to be a bundle. And because it's not flatly changing, it's not a bundle, even if I put this top Chern class in here, as I'm roaming around on my space, this thing in here jumps, and my number will not be invariant. So I need to modify everything. This is what algebraic geometries do. So this integral is modified by putting some different kind of class in here. This is something I'm not going to go into detail. It's going to be an obstruction bundle. And instead of this guy in here, okay, so let me also say, if you show this integral to a homological algebraist, they can realize this thing as collapsing of an element of cohomology and an element of homology. This is also another way of doing this. So if you put fundamental cycle of your manifold and you couple it with this guy, it's the same thing.
Is this space M like a stratified space? Like does this integral work like stratified?
Definitely it is. Yes, you can definitely do it. You fix the Chern character, in fact. Every time you fix the Chern character, you get a stratum of this gigantic moduli space of all possible evenings. Yes, so all possible stratifications do work. Okay, so this is like the way homological algebraists looks at this thing. And this is an element of homology theory of your manifold. It's the biggest degree class in homology, and this is the appropriate class in cohomology. And you will only get a number if the degree of this thing in cohomology and the degree of this thing in homology match. So algebra geometrically, also we do the same thing. And we can put this in here notationally, that's fine. But really what we mean is we put this class and we couple it with something we call virtual fundamental class of our space. Again, this is something in homology theory of our space. And this is something in cohomology theory. And we are coupling them together. And the degree of this class in homology theory is M. This is the fundamental cycle. Degree of this guy, though, in homology theory, this is not something like that. This sits in the degree of this virtual fundamental class is the expected dimension of your moduli space. Expected dimension of M. Okay? So algebraic geometers, when they say intersection numbers, what they mean is you have some ill-defined space that looks like maybe something really bad, but then they kind of try to realize this space as sitting as a zero section of a bundle, and this bundle has a, okay, so maybe I can call this a space M, and this bundle is going to be obstruction bundle. Its fibers at every point of the space capture obstructions to deforming things, not just their deformation, but obstructions to their deformations. And then this bundle has a natural section, and this section comes and intersects with the zero section. And this integral, this one, what it does is it counts the number of intersections. And these are the intersection numbers that we calculate. And this thing is the, by definition, is the virtual Euler characteristic of the space. In the case of a manifold and this one, this is exactly what it is. If you have the manifold, it sits inside this tangent bundle or cotangent bundle. This guy has a natural section and it intersects. And top Chern class of a tangent bundle or Euler class of a tangent bundle gives you the class of the zero locus of this section. And when you integrate over here, it means that you're actually counting. So we are doing the same thing in here. Okay? Any questions?
So this virtual fundamental class, should I think of it as like the sum of the fundamental classes and all the strata?
No. You should think of it as a perturbation of the fundamental classes. So here's what happens. This is the case of a manifold. But when you put this thing, and like this thing, this obstruction bundle, often it happens that this bundle, this section of this bundle, doesn't, if this is just fundamental class of M, you realize that obstruction bundle kind of falls inside here. So it doesn't meet this guy transversely. So you get some picture like this. Now differential geometers, who originally like Li and Tian, who were working on Vafa-Witten invariants, said that we have some situation like this. and they had some perturbation mechanism. So they were perturbing this section so that it becomes transverse, and then they were calculating the intersections. We algebraic geometers do not have this perturbation machinery. We cannot do perturbation to the section. What we do, in some sense, we perturb the base.
But you have these like.
You kind of, yeah, you can, if it is like this, we kind of do it like this. We change the base so that it becomes transverse, and then we count. And okay, this is all virtual because our basis is still M, but there is a class which represents a virtual base, which is this guy, and that class is this class. It sits in the homology of the base. It's not really representative of the base, which is ill-behaving, but it's the nice perturbation of the homology theory of that, such that this intersection is well defined. That's what we do. Okay, so this is what we are doing, and so in order to count Vafa-Witten equations, we just count, we just apply all of this to the modular space of these torsion sheaves. So I need to tell you, okay, so yeah, what to say? Well, I need to tell you these things, not really. So we define Thomas invariant. Thomas invariant for this modular space as the following integral. So dt of fix alpha with respect to the ample polarization on the base is given by integral of the appropriate homology class against the virtual cycle. So this virtual Euler characteristic that I just told you about has another name, and that's Thomas invariant. So this is the same as dt. It's an invariant associated to the moduli space of sheaves, which were studied by Richard Thomas and Simon Downs. Okay, so now I should tell you something which is core to this calculation. As you remember, our threefold is non-compact. The only compact part of this story is the base surface, and it's a non-compact space. So even though your sheaves are supported compactly on S, the moduli space of these sheaves is still non-compact. So whatever you want to do, whether algebraically or virtually or not, this integral cannot possibly be well defined if the base of this integration is non-compact space. So in order to fix that and get some proper space over which I can integrate, I need to use localization. So since MXH is non-compact, we use torus localization to compute the integral. So what is it we must do? This is very similar to Atiyah-Budd localization formula, but it has been modified for integrals against virtual classes. So the credit for this modification goes to amazing work of Rahul Pandaripandi and Tom Draper, who many years ago actually told us how to rewrite this integral when the base is a virtual class. So this will be actually defined like this. So we can write this dt, then we put a hat on it. It's given by sum over all torus fixed loci of the moduli space of integrals over these torus fixed virtual classes these are elements of homology. If you pick a homology class or a cohomology class, it also makes sense to talk about C star equivariant homology or C star equivariant cohomology. So I can put a C star in here, meaning that I'm interested in equivariant cohomology theory or homology theory. And then appropriate class divided by some kind of a Euler class of a normal bundle. So virtual normal bundle. Virtual normal bundle to this equivariant piece. I'm not going to tell you what is the virtual normal bundle because this is some algebraic thing and we don't need to go into the detail of that thing. Okay, so you have the space and then this is M and the torus fixed loci are given by things like this. M1 and M2, like that, and each one of them has have sheaves in them, which kind of understand the deformations of these objects that stick out in the normal direction. These sheaves are not going to be bundles because they have higher cohomologies. If they have only sections, H0 and nothing else, I would have called them normal bundle, but they're not. So they have higher cohomology, so it is more involved. What I'm putting in here is more involved. So they have H0 minus H1 and things like that, so that's why we call it virtual normal. So this is Euler class of some alternating sum of objects. And so basically this is the virtual normal one. And we are integrating all of that via localization. And what is the C star action in here? Again, it is the one that dilates the fibers. Okay? So let me make an example for you. Something that even in a commutative algebra course in first year of graduate school someone can understand, and show you one of these sheaves and basically make a relation between that and Higgs bundles that we get on the surface. So I'm interested, let's look at this picture, like that. Actually, let's reduce the dimension a little bit. So let's just look at one-dimensional case. So let's say this is the x-axis, and I'm looking at this line bundle on the x-axis. And let's pick some sheaf in the compactly supported coherent sheaves on this thing. So let's say this is the local coordinate y, and this is a local coordinate x. This is a non-compact surface, this is a non-compact fluid. Okay. So now let's look at some of these sheaves. So I would like to have a sheaf which is supported only set theoretically on this x-axis in here. What could it be locally? In terms of module theory, you look at the polynomial ring in this non-compact surface. Those polynomials are given by modules in local coordinates x and y. One of them is, in fact, a structure sheaf of x. You look at functions that are honestly supported on x. So what are those functions? Those are things that vanish along the y. And so there is an ideal that is generated by y. This means all the things that are generated by this coordinate. And this is basically the local picture for a module which is honestly supported on x. So this is structure sheaf of x-axis, if you like, in this picture. What is this thing? I mean, locally. Sheaves are locally modules over the ring. And this picture is actually just C of x. Because you kill y, and that's it. C of x. So you see, you will get C of x, and if you glue all of the C of x's on x, you will get this trivial bundle on x, which is all one. Okay? Functions, holomorphic functions defined on x. This is just O. Okay. This is first example. Second example, which is more exciting, is situation where you allow your sheaves to be supported on x, but you allow the support to be a little bit topologically more interesting. Maybe you fatten the base a little bit. So you can also look at same thing and look at ideal structure sheaf of a fattening of x, twice times x. What does that mean? By definition, that is locally if you mod out by an ideal generated by y squared. So these are all functions which vanish if they have a y square on them, but not y necessarily. If you calculate this again, a commutative algebra student tells you that this is not so hard to do. You will get C of x. These things are the things that survive. And you will get all the things that have x in them and y in them times a 1 factor of y and nothing else. Everything else that has y squared and above goes away. Okay, so you see, I told you that if I push forward things onto the surface, I get a graded module, right? You see, this is just a graded module sitting in degree 0 piece. This is also a graded module. It sits in degree 0. This one carries a torus weight because y is in this direction, and C star is acting on y. So the character of this thing as a module is +1. You will get this graded module down. Not only that, you also can see the Higgs mechanism actually appearing in here. When you have y in this thing, there is something you can do. You see that there is a coaction which is given by tensoring with the line bundle. So tensoring with the line bundle means here multiplying by the functions along line and the fibers of line bundle, functions by y. Let's do that. If I multiply the first guy, I will get the second guy. And if I multiply the second guy, I will get this thing, but this thing is going to be 0 because all of this is coming from modding out by the action of y squared. So this is going to be 0. Okay, now I have something in here and a map from it to here, and I can describe this by a matrix. The first piece goes to the second piece, and then the other terms are 0. And the first piece goes to the second piece by multiplication by y. And so this is your Higgs field T. So when you start from torsion modules or sheaves or D-branes that are supported on the base, but they are supported on an geometric fattening of the base, you will get, honest to God, Higgs bundle down. Okay? Now, if it's another practice that you say this to a student and tell them, can you start from here and go back to here? And that is very doable. You take the determinant of this thing and you get this minus lambda I, so the determinant equals to 0, and you will get this guy, and that's the spectral construction. It's just the same thing. Okay. So you will get that, you will get some one-to-one correspondence between Higgs bundles and torsion modules on this non-complex region. Okay. This is a good example because also it tells us that we are interested in not all the sheaves, but sheaves that are equivariant with respect to the torus action. We are interested in torus fixed loci. So I need to tell you, looking at this picture, what are those guys? If you start from something which is fixed by the torus, it better be that the Higgs bundle it induces down there is also fixed by the torus. What does that mean? This Higgs bundle is given as a morphism of graded modules. So let's call this thing E1. Let's call this thing E2. This is E1 tensor with L, and this is E2 tensor with L. I just tensored with L. E1 is sitting in degree 0, E2 is sitting in degree 1. E1 tensor with L sits in degree 1 because it has a non-trivial torus character. And this sits in degree 2. Even though it is 0, it sits in degree 2. In fact, if you make this 3, then you will get more terms, more interesting things there. Okay. If you start from a torus fixed sheaf, and I would ask you what is the torus fixed Higgs bundle down there, the only possibility is that the pieces which are getting mapped to each other have the same weight. So there is weight 0 and 1 there, and there is weight 1, 2 there. The only things that have same weight are these two guys. So, because degree 1 goes to degree 1. So it doesn't move. Both of them are being acted by the torus, but the whole package doesn't move by the torus. Same degree goes to the same degree. So if I looked at E1 plus E2 and E1 plus E2 times L, and I wanted to see what is the torus fixed part of this thing, this calculation shows me that it is going to be E2 times L, E2 going to E1 times L. Okay? So now we know what we should count. We are trying to count torus fixed Higgs bundles, so we start from Higgs bundle theory on the surface. We made a one-to-one correspondence to sheaves on the threefold. Then that moduli space is non-compact, but still we define our integral there via localization. So we realize now we should look at torus fixed ones. We come back to the surface, we look at the torus fixed ones on the surface, and these are given by things like this. Okay? And this is basically a flag. This is the flag that I mentioned. For instance, if rank of E1 is equal to rank of E2 is equal to 1, let's say I'm doing some kind of SU2 gauge theory on the surface, my modules that I start with in here are going to have rank 2. This one does have rank 2. If I wrote down in this picture, Chern character of this guy is equal to, this is the surface. Its rank is 0 because it's not supported everywhere. And its first Chern class is twice times class of the x-axis. And then it has some 1. Its Euler characteristic is 1. It's a bundle, trivial bundle. So this is one of those things. So rank over their own support is 2. And then you can see that this is rank 1 guy, and this is rank 1 guy. So let's say I have rank 1 and rank 1. Then I will get a sheaf of rank 1 mapping to a sheaf of rank 1 twisted with a line. Now there is a fact from algebraic geometry. Given a smooth complex surface, any torsion-free sheaf of rank 1 on S is given by ideal sheaf of points on the surface, ideal sheaf of functions vanishing on points on S with a twist. So the picture is, I have some sheaf of rank 1. This is given by an ideal of n functions vanishing on some number of points, n too many points, and they might have some, they might also vanish along some curves. So let's call it minus d2. It's a divisor. And it goes to here. This one also, by this algebraic geometric fact, becomes I n 1 of p, vanishing also along some curve times some L. So in fact, I can put, these are divisors, these are line bundles. I can put them, I can move them around. There is no twist. Line bundles are invertible sheaves. So I can actually think of this as I and 2p going to I and 1p minus d1 plus d2 plus L. Functions that vanish on n too many points, functions that vanish on n1 many points, and they have poles along the divisor like this. So pictorially speaking, I started from moduli space like this, and the torus fixed locus of my moduli space is giving me this interesting object on the complex surface itself. It's giving me a configurations of points and curves that are being nested inside each other. So this is n too many points, and this is n1 many points, something like that. Oh, n1 many points and 2 many points. Something like this. So when you look at the torus fixed locus of the moduli space of D4, D2, D0 branes, you get pictures like this. And we have a name for this one. If this guy wasn't here, the space that parameterizes points and curves on a complex surface, subspaces of a complex surface, or any variety in fact, that is a Hilbert escape. When you have nesting of these things, it could be that I can have a curve in here too, by the way. If you have this thing, that's a nested Hilbert scheme. So this is something that we studied in detail with Yao and my collaborator Ghulampour some years ago. As soon as we realized that this is a component in the torus fixed locus of moduli space of Vafa-Witten equations, we needed to calculate partition function of these guys. So then we just studied nested Hilbert schemes on surfaces. More to it is the following. If I started from higher rank sheaves, then in the last 5 minutes, I will tell you what happens there. So I have X, and I have S, and I have Q. I pick a sheaf in here, and I send it to here. It decomposes as sum of torsion-free sheaves there. Each one, they have rank Ri, and their sum of the ranks needs to be equal to rank of E. Now, how many components, possible components? Each time that I decompose the rank somehow, I can get one of those Higgs bundles if I want. Sometimes I don't, sometimes I do, like you saw. Sometimes you just get the trivial bundle, no Higgs map, or sometimes you get the trivial, some Higgs map. Okay. So the connected components of your moduli space are given by partitions of the original rank. So connected components of M of X, H, mu fix, C star are given by partitions of R. So when your rank R is equal to 2, the only possible partitions of 2 are 2 itself and 1, 1. This is essentially the example that I just did for you. Honest to God, D branes which are rank 2 supported on the surface, or the things that can have a decomposition into E1 plus E2, both of them being rank 1. If you go higher in rank, you will get more partitions. So for R bigger than 2, you can show that in fact the virtual class of this moduli space, C star virtual class, can become, or actually maybe I shouldn't talk about virtual class, let's just talk about components. This becomes a disjoint union of MC star R union MC star 1 and R minus 1. Sheaves which are decomposed into something rank 1 and something rank R minus 1. MC star 1, 1, 1 R times. This example. So MC star 1, 1, 1, 1, rank 1, 1, 1, 1, these are still on the surface. This gives you an R-fold nested Hilbert scheme. R-fold nested Hilbert scheme. And this gives you this is something that physicists call instanton moduli space. This is the instanton branch. So honest to God sheets of rank R on the surface. Everything else, which corresponds to the guys which decompose and they always have experienced the Higgs field, everything else is the monopole branch in the language of physics. So when rank is 2, you can calculate integrals on the instanton branch, and you can calculate integrals on the monopole branch, but the only possibility is 1, 1, which is the same thing as this guy.
What is this? I haven't seen this terminology.
Yeah, so this is...
Who calls it monopole? It says physicists, I don't know. I'm a physicist.
Yeah, it's probably it's one of those things that someone called it the monopole branch.
Someone they should
We
call
think
physicists.
math physicists called it, and physicists think we call it.
We don't call it that.
Yeah, but yeah, Tanzini and so on in Italy, and Boce and so on, they call it monopole branch. Boce is a mathematician. Sorry. Yeah, you're right. But I told it to my advisor who's somewhere in the middle, and he said it's okay. Yeah, but anyway, so now it is being called multiple branch. But if you
It's
say
not on multiples and fixed at different dimensions. They differ in dimension by 1.
uh-huh.
So whatever,
Then
these
we
are
don't
the
call
same,
it.
these are
Then
not.
I will tell everyone that we shouldn't call it a multiple branch anymore. Yeah, okay, that's you're the source. So another thing that I can just mention is that, okay, so integrals against this virtual class, so integrals in here correspond to Vafa-Witten invariants. This needs a proof, but I didn't talk to you about. We proved it, and actually originally Tanaka and Thomas also wrote this paper. They specifically targeted Vafa-Witten theory. They constructed the theory for these Higgs bundles on the surface and some notion of integration. We were looking at threefold invariance, but because our integrals are given by localizations, we just realized torus fixed loci of our moduli space exactly matches with them, with theirs, and our equivariant integral also matches with theirs. So even though we were counting sheaves on the threefold, like Thomas invariance, our invariance did also become Vafa-Witten invariance. Vafa-Witten partition function is conjectured to be a modular form. And this is the most amazing thing, really, and it still is open. In case of rank 2, when R is equal to 2, this part can be written as the sum of Seiberg-Witten invariants times some combinatorial coefficients for R equal to 2. Vafa-Witten becomes some partition function of Seiberg-Witten equations coupled with some combinatorial coefficients plus invariance of twofold nested Hilbert scheme. Nested Hilbert scheme.
You mean for SU2, right?
For SU2. This part, we proved is modular in some cases. We use the vertex operator formalism of Carlson and Lukunkov, certain integrals that we get integrals over this nested Hilbert schemes, but computations of which needs further machinery. So we use this vertex operator formalism and we prove the partition function in here modular. And so this one is modular. This would imply that maybe Seiberg-Witten theory doesn't have a modular function, but Seiberg-Witten invariance can be written in terms of modular functions. That's one thing. Sometimes, I didn't make examples, but sometimes multiple branch completely vanishes. For instance, if your surface is Fano, it vanishes. For K3, it vanishes. And then, this is amazing because it basically tells you that directly, Seiberg-Witten invariance directly can have some modular properties. And yeah, so other things for rank bigger than 2, my talk higher rank flag sheaves. For rank bigger than 2, you get this thing, which is the nested Hilbert scheme. Often it has modular property. This one, well, basically always gives you some kind of partition function involved in Seiberg-Witten invariance. But the goal right now that we are following is to show that the remaining parts, which are moduli spaces of configurations of sheaves that go like that, and they can have rank R1, R2, Rn, and the ranks are not necessarily 1, those things can have modular properties. Of course, it's not true, but in some cases it is true.
But Artan, couldn't they be iterated integrals? I mean, you could have, it's just the structure of the flag suggests that maybe there's an iteration. You start with something modular when the flag is one step.
It doesn't even work like that.
So it doesn't even work with one piece being
No.
modular.
No. Another fact I should tell you is that, because Kamran always likes computations, there is some cool result that Richard Thomas realized. When you increase the order of the gauge group, when you go SUR, he realized that these flags that you get, if they have ranks R1, R2, Rn not equal to each other, they don't contribute to Vafa-Witten invariance. So the first case, so for instance, SU2, you have Seiberg-Witten invariance and 1-1 invariance. SU3, you have Seiberg-Witten invariance. Then you have a partition of 1-2, rank 1 sitting on 1-2. That doesn't contribute to Vafa-Witten. And then you have 1-1-1. That contributes. The first instance where it kind of motivates the recent paper I wrote with Professor Yao is SU4. You have Vafa-Witten guy, that's the partition of just 4.
Yes.
Then you have 2, 2, and then you have 1, 1, 1, 1, 1. And 2, 2 has an interesting theory, which is completely new. Even in case of algebraic geometry, it's actually new. Moduli space of flags of rank 2 sheaves sitting inside each other, that's new. And that is something for which we formulated the notion of integral and things like that. So, yeah, thanks, and stop.
Can be multi-structural. Thank you, Artan. Question?
So, okay, so in the case of physics, we expected sometimes to be multi-modular.
Yeah.
And the multi-modular form is related to nestedness. So the lack of what they call, so the multi-modular form has a shadow,
Yeah. So if I add this
the shadow
holomorphic
part
thing,
is a holomorphic anomaly
yeah.
of the modular. So if you, for example, M2,
No.
del bar of M2 is not holomorphic,
No.
but del bar of M2 is related to M1 pieces.
Oh,
That's a shadow piece, the
Oh,
complex
cool.
conjugate of that.
Oh, I see.
So there's an interesting, so for rank 2, the example of rational elliptic surface, which is called the E-strings story. In that case, we actually have the particular structure of 2 and the 1, and in fact it generalizes to n splitting up to n minus k and k. So in other words, the splitting, the del bar of the highest one splits to 2 pieces, to n minus r and n, r minus n and n pieces.
I see.
And that is the shadow part in the
Cool.
case of that. And that is actually interesting to try to see if you
So
can
for instance, for 4, the 2, 2 part is the
should you have computed, in other words, already.
Yeah.
So the anomaly piece would have been that. That's in the cases that you have holomorphism. So this happens when your surfaces has positive curvature,
I see.
like rational elliptic surface and so on.
Okay.
So for the cases that your things can fly off the surface, that's different.
I see.
You will not get multi-modularity, it is expected only in these cases. The analog of B2 plus is 1 kind of thing.
Cool. Okay. That's
Have anybody computed these in any cases?
recently. Tanzini put a paper on archive and he sent me this email. I will send it to you. So using some different methodology, I mean physics actually.
Well, we use physics to compute them.
Yeah.
But
So
if you use physics, that's already done. I'm just asking if the mathematicians.
mathematician, we are trying this, and soon I will.
Sorry, we did rank 2 case. You may have done higher rank case.
Yes. So for rank 2, we haven't done any computations yet. We are doing some computations on toric project surfaces. Also, we are just a simple model. We are trying to do this on curves. Moduli space of flags of sheaves on a complex curve. And that also is not related, of course, to Vafa-Witten theory, but it has modular properties. So soon, my postdoc and I will actually be working on it. Maybe in the spring I will talk about it. Yeah. But no, it's very difficult to do this calculation. We just basically defined a well-defined integral in here because in order to show that you have an invariant from math point of view, you need to say that this integral is well-defined. So this deformation obstruction complex needs to exist first. And so we figured ways, situations that we can define it. Using
So the nested structure in the
nested one is completely done.
No, the nestedness structure of these.
Yes.
It's not just disjoint, I'm trying to say, in
Yeah.
the sense that they go together is, in the language that we do, comes from the boundary of moduli space, they touch. And that's why del bar, so naively holomorphic anomaly means that you expect it to be holomorphic. But the fact that it's not is the boundary contribution coming from splittings, from the boundary of one of them where MR decomposes to the different ranges.
I see.
So that's why you get this contribution. So it should not be disconnected computations. Computation should somehow be related.
I see. Okay.
And the other thing is that in the context of physics, we expect these things to also have a refinement. It's not just numbers, but they should be SL2 characters.
Oh, I see.
So roughly speaking, the moduli space you expect to have a Lefschetz action and this homology.
Mm-hmm.
And that it gives you further structure to the numbers. It's not just the counting of the dimensions, but the structure of a SL2 action.
I see. That we haven't studied.
In other words, that of course should go to Donaldson. Also, the T invariant should also have this refinement.
Yeah. So yeah, we haven't defined a refined version of these things. But this nestedness structure that you're talking about, I was also told about this by coach. He is actually also, he told me that these things are not really disjoint.
Right.
There's
It's
certain
crucial,
duality actually between them, which I haven't really understood yet.
You mentioned that you wanna pose some open questions, need helpful physicists.
Yes. Open question is, can you show me how you calculate this theory? I give you. So let's S be toric projective surface P1 times P1 or P2. And let's look at the modular space of vector bundles even if you like. P1 to P2, rank 2, rank 2, where the map is injection. Can we calculate partition functions of these things?
Rank 2 to rank. What do you mean?
Rank 2 to rank 2. Both of them are rank 2, but they have different churn characters. So this one has rank 2, gamma 1, and 1. This has rank 2, gamma 2, and 2. And as a map of modules, this map is called inject. It's not an isomorphism. They don't have the same Hilbert polynomial. It's not an isomorphism. And they are, is there any instance in physics that people calculated this kind of thing? And you see, you have all of these nice tori here. C star square, C star square. How do you calculate partition functions of this kind of thing? Is there any physics model?
You can come up with physics model. So you want to, it's not that n equals to Fourier millions. Since you have a map from one, you have some SU2 times SU2 gauge theory.
That's
You
right,
have
that's
pi fundamentals between them, and you're talking about these pi fundamentals between them, which is
That's right.
so it's not n equals to 2. It's more in the category of like Simon-Witten rather than n equals to 4. So I would not expect, for example, modularity in this case. But
Yeah.
in general, it's along the lines of half the supersymmetry.
So there is work on this. People
I'm not saying there's a work. I'm saying that that's the way I would start for trying to study this.
Yeah, I'm not sure. I'm not saying that we are certain that these things. I mean, this whole right-hand side eventually is going to be modular form, but there is a priori no reason that each piece is a modular form. Of course, I mean these numbers are split apart into different components. But even just calculation of something like this is very interesting.
But Artan, you said this is the 2-2 part that will contribute to the bond.
Yes. This is the 2-2 part that contributes. Even if it is not modular form, it's fine.
Sure.
I just want to be able to calculate numbers and check with physicists to see.
Any more questions?
Let me say one thing.
Oh, so sorry. So
Yeah.
it's clear that I should have said it's clear from the physics why this question arises. You're splitting, of course, which is probably the same reason you get into. Maybe you have 4x4 matrix. The off-diagonal blocks is
Yeah.
what you're talking about.
Yes, that's right. That's exactly right. And one other thing which is mysterious to me is that I've been interested in looking at moduli space of solutions to Kappus-Witten equations. These are Higgs bundles like this, but unlike your pairs, they have a tangent bundle on the surface. So if I do a spectral construction, ambient geometry is a fourfold. And fourfold invariants are still under investigation in the world of algebraic geometry. Really, some kind of different machinery is needed. We calculated a situation where our base surface is an elliptically fibered K3, and we calculated partition function together with Diaconescu, if you remember, and we computed exactly same Vafa-Witten partition function. Is this coincidence, or is this expected?
I think there's the local model for the 4-fold and 3-fold would be the same in those cases because you have too much symmetry for K3.
But our fourfold was a total sum of 2 bundles on the surface, like L1 plus L2. Okay, but you're saying still symmetry is so much
just
that
right.
it is kind of.
More comments? No, let's thank Artan again.
خیلی خیلی متشکرم. He's really amazing.
Yes, yes.
He writes very good. He wrote solid normal, but actually
We also talked about it.
Because everything is like the trend of the language, right?
میفهمم.
Well, if you have